Good morning, everyone, and welcome to the last of our Michigan Concrete Association winter webinars that we did as a result of the ice storm on the second day of our conference in Kalamazoo back in February. And we're happy to have Jeff Girard here today to talk about engineering ethics. It's our topic this morning. And Jeff is an affiliate partner of ours, is with the American Concrete Pipe Association. He's the Michigan engineer, so the director essentially of the Michigan Concrete Pipe Association. He's been in that role for about 6 years so far at MCPA, or I should say ACPA. CPAM, I think, is what your acronym is, Concrete Pipe Association of Michigan. And it has prior experience with this reinforcing steel industry and other, drainage pipe products and things like that. So we're happy to have Jeff here today. He's got a Bachelor of Science in Civil Engineering from Lawrence Tech University. So he's a Michigan, went to school here in Michigan and has stayed in Michigan. And we're happy to have Jeff. I've seen this presentation before myself, so great presentation, a good refresher on engineering ethics overall and in general, and should satisfy at least one of your 2 hours of engineering ethics that's required every 2 years for your PE renewal cycle. 2 hours of those 30 continuing education hours do need to be on engineering ethics. So we're happy to at least provide one of those hours for those of you this morning. And Jeff, I will let you take over and share your screen and take it away.
All right. Am I up and running there, Steve?
Yep, looks good.
Excellent. All right. Thank you guys for having me and for attending. I'd like to really just jump right in. There might be a couple points where we're asked a couple questions. If you could put some notes in the comment section or respond to it, maybe we'll get a little feedback there. Let me go ahead and jump right in. My name is Jeff Girard. I'm a director of the Concrete Pipe Association of Michigan. Over the next hour, we're going to be exploring the many facets of professional ethics, but with a primary focus on engineering ethics. First, we'll cover the basic philosophies behind professional ethics, the history, both the profession and the ethical codes, the differences between micro, macro, and meta ethics, the public perception of our profession. We're going to cover codes of ethics for NSPE and ASCE and why a code of ethics might be necessary at all. We're not going to dig into every line item, but we're going to hit some key categories and discuss those in a little bit of detail. We'll look at the distinctions between liability and professional accountability, and how can we incorporate the ethical canons from professional ethics into our daily practice. Last, we'll review some current events and how professional ethics push us to be good stewards of our environment, to cultivate our continued education and professional development. And we'll take a brief look at a couple of case studies along the way and kind of comment on some things in the last 5 to 10 years that have gone on. All right, there we go. All right, so let's begin with a common definition of ethics, just to make sure that we're all on the same page and kind of using the same terminology. Merriam-Webster defines ethics as the discipline dealing with what is good and bad, and with moral duty and obligation. Ethics can also mean a set of moral principles or a system of moral values. Within the broad spectrum of ethics, there are a great many disciplines. 3 major areas of study within ethics recognized today are metaethics, or the theoretical meaning and reference of moral theories and how their truths are determined. Normative ethics, which is the study of moral action. And applied ethics, or what a person is obligated or permitted to do in a specific situation. As we explore engineering ethics, we'll be looking at various case studies which will involve looking at the applied ethics of each case. If asked about the origination of our profession, many engineers will kind of look back at some of the ancient architectural wonders of the world, such as the Great Pyramids or Roman aqueducts. Yet, really, the term engineer wasn't coined until the 1300s. One engineer historian, Henry Petrosky, claimed that engineering is as old as civilization, but the concept of the engineer as distinct from architect or master builder is relatively modern, claiming at the same time that there were in ancient times individuals whom today we would call engineers. It should be noted that the term engineer and engineering didn't appear in the lexicon until after 1300. This post-1300 activity was defined by Thomas Treadgold of the British Institute of Civil Engineering as the skill of directing the great resources of power in nature for the use and convenience of humans. Until that time, the profession of engineering was more of a trade or practice in architecture. The first people to be referenced as engineers were actually soldiers engaging in engineering tools of war. Trebuchets, as shown here, siege towers, and artillery. But until 1676, engineers were simply soldiers in the infantry. But in 1676, Louis XIV built a standing army of 300,000 with a specific engineering battalion known as the Corps de Génie. These corps were important for the future of engineering because as a permanent institution, rather than just isolated individuals, it was able to keep better records, accumulate knowledge, skills, routines, those kind of things. More importantly, these skills could be efficiently passed forward. The first engineer without military association was Englishman John Smeaton, who declared himself a civilian engineer in 1771. As we continue moving forward along our timeline, we see that the American Society of Civil Engineers was founded in 1852. In 1883, construction on the Brooklyn Bridge was completed. 1889, the Eiffel Tower was completed. In 1914, 60 years after their foundation, ASCE adopted their first code of ethics. AIEE had adopted theirs in 1912, ASME in 1914. Each of these three codes was less than a page in length and stressed that the engineer was to act simply as a faithful agent or trustee. These first codes of ethics were primarily focused on loyalty, without any mention of public welfare. In 1926, LA County Public Works Department completed the St. Francis Dam, which was built at an elevation of 1,800 feet above sea level and 175 feet above the stream bed, with a capacity of approximately 32,000 acre feet. Just before midnight on March 12, 1928, the St. Francis Dam catastrophically failed. This sent 12.4 billion gallons of water surging down the canyon. The largest piece of the broken dam, weighing approximately 10,000 tons, was found about 3/4 of a mile below the dam site. The immense wave of water left destruction and over 400 deaths in its tracks. That same year, the LA County Public Works Department had also commenced the construction of the San Gabriel River Dam. Perhaps due to the media surrounding the catastrophic failure of the St. Francis Dam, that same year, 2 engineers exposed the contractor of defrauding LA of $700,000. ASCE investigated the whistleblowers, and subsequently, both engineers were stripped of their ASCE membership in 1932 for, quote, bringing on a brother engineer injury due to his reputation. In 1934, the NSPE was founded, but no official code of ethics was adopted until 1946. This ethics code made public welfare a primary duty for engineers. In 1972, during the construction of the Bay Area Rapid Transit Tunnels, 3 engineers who worked for BART expressed their concerns over safety defects in the design and construction of the train system. The concerns were ignored at first, and eventually they went to the press, which led to their dismissal. Although this case was similar to the 1928 San Gabriel River Dam case, rather than being punished for their engineering, rather than being punished by their engineering association, they were applauded. The IEEE, or the Institute of Electrical and Electronics Engineers, supported the three engineers publicly in 1974. They actually received some compensation from the contractors and were given public recognition for their efforts to protect public safety. In 1981, NSPE adopted its first distinct ethics codes with a short list of fundamental canons, the first of which is to hold paramount the safety, health, and welfare of the public. The codes of ethics for each of the major engineering societies have continued to evolve as needed through member involvement. About 2 or 3 years ago, ASCE updated their code of ethics. And to be honest, when I first started giving this presentation about maybe 8 months ago or something like that, I didn't even realize that ASCE had recently reworked their code of ethics. So I had to scramble a little bit to bring things up to date. But it's worthwhile for them to go through and expand upon some areas and kind of realign their ethics. So I was very pleased to go through it and kind of learn a little bit more about it. All right, let's look at some definitions of micro and macro ethics. First of all, macro and micro are not intended to suggest big and important versus small and unimportant. A micro ethical question refers to the behavior of an individual, whereas a macro ethical question refers to the responsibilities of a profession as a collective group. Initially, the codes of ethics formed by the major engineering societies had a focus on micro ethics, or the behavior of the individual. But gradually, there's been emerging consensus in the professional engineering community that personal ethics are not enough. Professional ethics must also include an analysis and action on institutional action and policy. In other words, the evolution of engineering ethics has moved to incorporate macro ethics, or the responsibilities of a profession as a collective group. As Norm Augustine, a former CEO of Lockheed Martin, wrote in The Bridge, it's a publication, National Academy of Engineers, quote, "The bottom line is that the things engineers do have consequences, both positive and negative, sometimes unintended, often widespread, and occasionally irreversible." Let's look at an example provided by William Wolf of the NAE. In his keynote address to the National Research Council, Dr. Wolf looked to the medical profession for an example of micro and macro concepts. The Hippocratic Oath, which focuses on the behavior of individual physicians, is similar in a lot of ways to the ethical codes of professional engineering societies. But medicine is also grappling with some micro and macro questions. For example, allocation. If there are not enough organs for all the patients who need transplants, who should get them? If there's not enough medicine for all the patients who need it, who should get it? If there are more patients than there is time for the physicians to treat them, who should be treated and on what basis? These are not questions for an individual physician to decide for himself or herself. They're questions for the profession, where they must grapple with, or maybe society guided by the profession. Once a decision is made, a physician decides to follow that decision or not to follow it. That becomes a micro-ethical question. Metaethics is a more difficult concept to describe. While microethics explores what is moral for that individual, and macroethics is a study of the responsibilities of the entire group, metaethics is an exploration of what morality actually is. One could say that micro or macro ethics can be learned by memorizing a set of rules. The beauty of metaethics is it forces each individual to learn how to make the moral decision on a wide spectrum of cases, which, as we all know, are seldom black and white in real life. Let's look at how the general public perception, kind of how they look at our profession. In 2012, Gallup performed a public opinion poll. It's pretty interesting. But they looked at the honesty and ethical standards of people in the fields below in this table. There's some very interesting results if we go through some of this. Maybe unsurprisingly, the very bottom category is car salesman. Just points above it are members of Congress. Again, not much of a surprise here. As we move up higher, we find clergy given a rating of high or very high at 52% of the public. Then engineers are near the very top of the list with a rating of 70% in the very high category. And then nurses top the list at 85%. Now, this is kind of a little bit of fun. You can have a chance to point your finger and maybe claim some ethical superiority, but it also really begs the question, does public perception drive us to achieve a higher ethical standard? Engineer scores have steadily increased since the poll began in 1976, with the exception, you'll see here in the bottom right, of a drop in the poll, about 5% in the 4 years between 2012 and 2016. Think about if there's anything that strikes you that could have caused a little bit of a drop off in the perception of engineers. There's a few theories about why public trust in engineers might have dropped just before the poll was taken in December of 2015. You might remember this commercial. This was from the Super Bowl from January of 2014. Let's take a look at this.
Hey, Darcy, look. 100,000 miles.
So?
It's a big deal. What if I told you that every time a Volkswagen hits 100,000 miles, a German engineer gets his wings?
Doobie doobie doo. 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 Doobie doobie doo.
I hate these wingy thingies.
Yeah, Dad, and I'm sure at 200,000 miles, rainbows shoot out of their butts.
Volkswagen has the most vehicles on the road with over 100,000 miles. That's the power of German engineering.
All right, so hopefully the sound came through okay on that. That was really a genius bit of marketing for VW. You know, their engineers getting their wings for a car reaching 100,000 miles. But then just 1 year after VW gave their automotive engineers angel wings, the EPA found that many VW cars being sold in America had what they called a defeat device, or software in diesel engines that could detect when they're being tested. It would change the performance in order to improve the results. They dubbed this the diesel dupe. VW eventually owned up to the deception at a cost of, they say, as much as $87 billion with a B. The Society on Social Implications of Technology president, Greg Adamson, discussed the 2015-16 VW deception and the rift that such events create between the engineering community and the general public. He said, in addition to the anticipated financial impact of the company, Adamson writes, it was a setback to the credibility of technologists, one that brought ethics to the forefront. Adamson insisted that in situations such as these, an engineer's primary loyalty should be to public interest and not his or her employer. So this kind of pushes us into the actual codes of ethics of, we're going to look at NSPE and ASCE, which do now share quite a deal, great deal in common. It's the NSPE Code of Ethics and its layout. You can see they've got a couple categories with supporting documentation that leads into their canons. We start looking at the preamble. The NSPE Code of Ethics addresses the overall need, goal of the code in this preamble. Engineers hold a vital position in society which directly impacts the public, and therefore engineers must serve in an honest, impartial, and fair and equitable way. They must dedicate themselves to protecting the public health, safety, and welfare. You'll notice that this is a common theme among many different engineering societies. As we move into the fundamental canons from the code, basically they're holding public safety, health, and welfare above everything else. Again, kind of a common theme between the different organizations. Only provide design in your area of competence. Only issue objective and truthful statements. Act for the client as a faithful agent. Don't be deceptive. Act responsibly with honor, ethics, and according to the law. Section 2 of the code gives the rules of practice, which provide more detail for each of these canons. We'll look at these, but for the sake of time, we're not going to dive into all the text here. The first rule of practice is that engineers must hold the safety and health of the public as their highest ethical goal. Perform service only in areas of their competence. This is a rule that, like, engineers have been taught since day one of college, that a professional engineer must only perform their duties in their area of study or experience. Engineers shall issue public statements only in an objective and truthful manner. This canon likely causes a great deal of heartburn for any engineers who decide to run for political office. Act for each employer or client as faithful agents or trustees. Canon 4 requires the engineer to act in a professional manner and in such a way that the client can put 100% trust in them and their designs. Canon 5 really just simply states that an engineer should avoid deceptive acts. In other words, a professional reputation should be built on the merits of one's own services, and that engineers shall not compete unfairly with others. And in section 3, got the professional obligations. The professional engineer really include several major areas for guidance, including engineers shall hold themselves to the highest standards of honesty and integrity, and engineers shall strive to serve the public interest at all times. Like many others in college, I chose to swear an oath participating in the Order of the Engineer membership ceremony, often symbolized with a stainless steel ring to be worn on the pinky of the dominant hand. The NSP oath is known as the Engineer's Creed. The pledge entails to always give one's best performance, participate only in honest work, to live and work by legal framework, the highest standards of professional conduct, to place honor before profit, and place the public welfare above all other considerations. In October of 2020, ASCE updated the layout and look of their code. So let's look at that for a few minutes. The new version of the code does have a similar layout to the NSPE code, with some canons that follow closely and some supporting text to give clarity on how the code of ethics should be interpreted as far as the ASCE code of ethics is concerned. Again, starting with a preamble for the conduct expected of engineers and a list of fundamental principles that must be followed. You may notice that the main bullets in the preamble closely follow those listed by NSPE, with an additional point found in the second bullet: to treat all persons with respect, dignity, and fairness in a manner that fosters equitable participation without regard to personal identity. The body of the code is broken down into 5 major categories: society, the natural and man-made environment, professional integrity. This category is kind of professionalism, clients and employers specifically, but professionalism when dealing with their clients and employers. And of course, the peers, responsibility when dealing with others throughout the profession. In today's world, it goes almost without saying, but as we explored earlier, it should still be said that engineers must hold the safety, health, and welfare of the public above all other considerations. Kind of wrap up this section with a case study, talking a little bit about the first canon regarding public safety, and take a look at the legal ramifications from the I-35 bridge collapse in Minnesota. It's especially fitting. On August 1st, 2007, the I-35 bridge over the Mississippi River in Minneapolis collapsed during the evening rush hour. There's more than 1,000 feet of the bridge falling into the river below. At the time of the collapse, traffic was congested, normal rush hour as far as traffic was concerned, and also congested from fans heading to a Twins game. 111 vehicles were on the section of bridge when it collapsed. Along with members of the construction crew working on the deck, their equipment, their supplies, ended up killing 13 people and injuring 145 more. And really the loss of an important interstate bridge, which had a major impact on the Minneapolis economy and day-to-day activities. The NTSB investigation found that the cause of the collapse was an undersized gusset plate, U-10. This photograph taken before the collapse shows the gusset bowing under the increased loading on the bridge. The maintenance activities taking place at that point had stored 575,000 pounds of construction materials to be used for resurfacing the deck. It was directly over this U-10 gusset plate. The investigation further found that the plate had been undersized during the design phase 40 years earlier, and that none of the subsequent bridge inspections had caught the error or seen the symptoms of the impending failure. Despite state and federal guidelines and regulations, the Minnesota Department of Transportation inspectors and engineering groups hired to inspect the bridge all failed to act. As a result, the engineering, design, and inspection firms, the construction company working on the bridge at the time of the collapse, and the state of Minnesota all faced some enormous liability issues. After 5 years of litigation, Jacobs Engineering settled with MnDOT without any admission of wrongdoing. Jacobs had actually just purchased the engineering company, which designed the bridge in 1999. So they ended up settling for just under $9 million. URS paid $52 million in a settlement, even though it was not involved in the design or building of the bridge, but it had performed maintenance and consulting on the bridge since 2004. So how can we use these codes in our daily lives? Many engineers consider the codes as simply references, which can be looked at occasionally, or in this situation, it's used to fill up some space in an ethics presentation. However, there are helpful ways which the codes of ethics are very helpful. Let's look at how the ethics codes could be used in a legal situation. In the Volkswagen emission testing scandal we discussed a little earlier, at various times during the company investigation, Volkswagen executives suggested that the engineering staff, they were the ones that were largely responsible for the problem. And this is just a year after the commercial in which they portrayed their engineers with angel wings. Those claims left the engineers vulnerable to termination of employment and legal claims raised by Volkswagen, government authorities, and by individual consumers harmed by the scandal. Volkswagen management, in effect, attempted to make company engineers scapegoats for this major corporate scandal. If the VW engineers had created a written record using codes of ethics to document their concerns and objections, that record could have been used to counter the unfair corporate allegations and to defend themselves from legal liability. The federal government and 17 states provide protection for individuals qualifying as whistleblowers. A whistleblower despite the negative connotations. Another term you might hear is a leaker, is defined as an individual who alerts the appropriate legal authorities about behavior that the individual reasonably believes to be illegal or fraudulent. Depending on the jurisdictions, whistleblower protections can extend to reports of action that threaten public safety, public health, or the environment. Whistleblowers are generally protected against employment termination and other retaliation or harassment by employers and other employees. Codes of ethics can help engineers pursue their own legal action against an employer or client if the engineer faces repercussions as a result of expressing their concern or refusal to follow orders. Many states, the courts recognize claims of wrongful termination raised by employees against employers, but employees really bear the burden here. They have to demonstrate that the termination of the employment was illegal. So documentation that the engineer raised reasonable concerns of illegal, fraudulent, or potentially harmful conduct by the employer really strengthens the engineer's case by demonstrating that the engineer's actions were motivated by reasonable professional concerns, an argument that is made much more compelling through reference to specific codes of ethics. The engineer presents a stronger case that termination was retaliatory and not justified by an insubordinate. By insubordination, excuse me. While we're talking about whistleblower protections, it's a good idea to know your rights. In Michigan, both federal and state law can apply to the question of protecting someone who reports on dangerous or unethical behavior. The Whistleblower Protection Act of 1989 provides protections that are largely limited to reports of misconduct associated with workplace health and safety, as well as environmental protection. But under some circumstances, whistleblowers who report government contracting fraud or misconduct or security law violations may also qualify for federal whistleblower protection. Some states provide whistleblower protection. A federal agency violates the Whistleblower Protection Act if the agency authorities take or threaten to take retaliatory personnel action against an employee because of disclosure of information by that employee. Michigan whistleblower law protects the employees of public and private employers, allowing them to file a complaint with a public body, such as law enforcement, a state agency, or a member of the judiciary. Not all states have the same whistleblower laws, and in fact, many don't have a law about whistleblowing protection at all. Make sure you check the applicable state laws and codes. Make sure you're properly informed on the Whistleblower Protection Act in Michigan or wherever you're doing business. In many cases, moral responsibility runs parallel to legal liability. Liability is simply defined as action that is deserving of punishment for causing harm. Tort law is the part of the legal system that addresses legal injuries or wrongs in the course of practicing a profession. It is also known as the malpractice law. Tort law considers the degree of harm and gives weight to the cause for inflicting harm, which can be on one of these three levels: intentional harm, reckless harm, and negligent harm. In liability cases against professionals, rarely any professional is proven to have caused intentional harm, and really very few cases result in proving that harm was caused recklessly. Most of the professional liability cases would reveal that the cause of harm was negligence or negligent harm. Conforming to professional standards helps protect the public and the engineer from possible accidents and safety concerns, as well as legal ramifications. However, engineers should be aware of the boundaries and limitations of their legal and professional responsibility. This is particularly important when problems occur, resulting in grave legal and liability questions. To fulfill this professional responsibility, engineers can follow a model known as reasonable care. commonly defined as that level of skill and competence ordinarily demonstrated by professionals of the same discipline, practicing in the same locale and faced with similar facts and circumstances. Tort law defines and accepts a professional standard of care or reasonable care as that which relies on, but not restricted to, I'm going to read this part, the standard operating procedures of a profession and ordinary job responsibility. Accordingly, this definition is also open to some interpretation and subjectivity depending on the circumstances and evidence in the case at hand. Therefore, most codes of ethics support a broader principle of care that goes as far as recommending that one should avoid even contributing to producing harm by action or inaction. Codes of ethics emphasize that engineers are privileged to be able to see the potential for harm and be able to prevent it. How might we incorporate our engineering ethics into everyday practice? One seemingly easy answer is you take baby steps. Measuring one's ethical decisions each day not only helps to raise personal awareness, but also to increase the likelihood that integrity and honesty become daily cognizant habits. Even little things can make a big impact. Take, for example, those among us who are chronically late. While the late party is often able to look outside for excuses for their tardiness, be it traffic, missed an alarm, Google Maps took me to the wrong place. Chronic tardiness is frequently interpreted by those stuck waiting as a disrespect of their time. Persons who is perpetually late is thought to be saying that their time is more important than yours. This seemingly insignificant part of everyday life can have detrimental and lasting effects on one's professional reputation. Imagine how much more detrimental the ethical dilemmas that are related to the fundamental canons could be. William Wolfe, president of the National Academy of Engineers, stated, "We need to think ahead about how our actions might affect people for good or ill. We must be prepared to practice in an ethical way as the circumstances change." How our personal and professional behavior affects people is often seen as a reflection on our own integrity, honesty, and reliability. These three principles are the building blocks of an ethical person. Integrity is defined as adherence to moral principles and soundness of character. So in other words, someone who exhibits integrity can build a reputation as following moral principle. This is often visible from outsiders. Honesty is defined as sincerity, fairness, and freedom from deceit or fraud. Basically, someone who doesn't lie and isn't deceitful. And reliability is again visible by the outsider, someone who portrays trustworthiness, predictability, and dependability is reliable, and the type of professional you probably want on your team. In the context of practicing professional engineering, many regulations and professional expectations rely on and deal with the concept of integrity and honesty. There's a few examples here of situations. I could include the following. Got full disclosure. The Engineering Code of Ethics stipulate that information needed for informed consent of an individual should be provided in full. The order of priority is always to protect the public and society, then the client, and finally the engineer's interests. Confidentiality. Confidential information will reach the engineer either directly from the client or by accidental discovery during the course of performing work for the client. This information can be subject to abuse in two forms. The first form is when confidentiality is broken while the action is not warranted. And the second form is when confidentiality is not broken, although the higher obligation to the public requires it. And last, we've got conflict of interest. This situation exists when a professional judgment is subject to influences, loyalties, or other interests. Conflict of interest also tends to make the judgment less likely to benefit the client then the client is justified in expecting. All right, so let's look at an actual case study from the NSPE ethics files. Engineer A works for his or her state DOT and is an in-house project manager on a project. The contractor for the state project submits a change order to Engineer A for approval. Engineer A thinks the change order is due to the contractor's faulty work and will not sign the change order. The contractor then contacts Engineer A's supervisor, who directs Engineer A to sign off on the change order. Note that the supervisor is not an engineer. Is it ethical for Engineer A to sign off on the change order?
For
According
those of you
to
listening in, oh, sorry to interrupt.
That's okay.
Feel free to use.
I was watching the chat and stuff.
Yeah, feel free to type it in the chat or in the Q&A, or click the raise your hand button. And Jeff, we actually, if you raise your hand, I guess we'd have to unmute you, but it's easiest just to type it in the chat or the Q&A. So anyways, go ahead, Jeff.
Thanks, Steve. Thanks. So in this case, according to NSPE, no, it would not be ethical. In fact, Engineer A has an obligation to report up to the state DOT authorities. All right, let's move into environmental stewardship. Principles of sustainable development is an important aspect of the first fundamental principle of the ASCE Code of Ethics. And NSPE considers it a professional obligation in order to protect the environment for future generations. The environment has become such a hot topic in the, kind of the political discourse that many engineers, we avoid the discussion in some ways for fear of offending or losing credibility. And yet evidence is clear that the actions of engineers can have profound effects on our world, for both good and bad. Both ASCE and NSPE lay out their references to the environment in a very detailed and elaborate fashion. The references are some of the most explicit references to the environment in any engineering code of ethics. The words create and adhere used in the ASCE Code of Ethics level of action would at a minimum require both personal compliance, but also likely informing clients about the consequences of violating sustainable development and possibly informing authorities about violators of sustainable development. Got to read that part, make sure you get it right. One option regarding the goal of sustainable development is to become a member of the Institute for Sustainable Infrastructure. This is just one organization, but this institute was founded jointly by three societies: ASCE, ACEC, and APWA. The ISI is intended to act as a unique community of organizations and individuals who are involved in the planning and design of infrastructure. The single purpose of the organization is to develop and maintain a sustainable rating system for all civil infrastructure. That program is called Envision. Envision is the framework that includes 64 sustainability and resilience indicators called credits, organized around 5 categories. These include a vast array. I'll read a few of them. Quality of life, leadership, resource allocation, natural world, climate and resilience. These collectively address areas of human well-being, mobility, community development, collaboration, planning, the economy, materials, energy, water, conservation, ecology, emissions, and resilience. These indicators collectively become the foundation of what constitutes sustainability in infrastructure. Through membership in the ISI and utilizing the indicators for resilient and sustainable design, engineers can begin to have a true impact on their communities in a positive way. And really, I shouldn't even say begin, because I know a lot of folks are already having an impact on their communities in a positive way through their engineering, but really just kind of raise the level or continue to improve and learn as we go. Let's kind of forget about the toxic climate change that can often get us off course, and really we could start talking about something called future proofing or resiliency. Future proofing is a term that provides design professionals with a target to adjust our behaviors. As an example, we can no longer simply continue to design for 100-year storms when they're happening at a much higher frequency. One of the keys to future proofing infrastructure is resilience. AASHTO defines resilience as the ability to prepare, plan for, absorb, recover from, or more successfully adapt to adverse events. In other words, resilience doesn't necessarily mean that the infrastructure will sustain zero damage during an emergency event, but that it can absorb the impact and quickly recuperate for emergency personnel or even full operation. FEMA has found through a recent case study, a recent study, that for every $1 invested in disaster mitigation, society saves $6. When looking at flood mitigation, that return on investment jumps to $7 for every $1 spent. The Pew Charitable Trust recently found that 40 to 60% of small businesses never reopen after they're impacted by a disaster, and 90% fail within a year if they aren't able to reopen within 5 days of the disaster. This means that resilient infrastructure is absolutely critical to the life and well-being of small businesses and communities across the country. Let's consider a solution to future-proof infrastructure after a national disaster has hit. In 2011, Hurricane Irene damaged more than 2,000 culverts in Vermont. One of those was a large diameter corrugated metal pipe culvert, which was replaced with a precast arch box on the Townsend Dam Road. To rebuild with resilient infrastructure, the washed out CMP culvert was replaced with a precast structure prior to acceptance by the Federal Emergency Management Agency, or FEMA. Initially, FEMA ruled that the box was an upgrade. VTrans defended the municipality's decision through 2 appeals, leading to the announcement by the governor of Vermont and the Vermont congressional delegation on March 22nd, 2013, that FEMA would agree to fund the replacement. This ruling set a precedent that could allow dozens of Vermont culvert replacements to qualify for funds from FEMA. And it raised an excellent point. Sometimes persistence can pay off, and if your emergency replacement is initially deemed an upgrade, you have the ability to appeal a second time. Senators Leahy, Sanders, and Welch were also helpful in convincing FEMA to accept the change in material. As they stated, it makes no sense to use federal tax dollars to put back in place the same culverts that just blew out. Or to put it another way, constantly replacing failed infrastructure with the same product that previously failed is the definition of insanity. The ASCE code requires professional development, as does the NSPE professional obligations. Fundamentally, engineering is the application of science and the utilization of new scientific discoveries into products and services that help improve human life and human endeavors. Consequently, explosive rates of engineering and technology developments are being experienced every day. I think we all see that through the news, through the internet. The downside to this is really kind of how unprecedented and how high speed the discovery and updating knowledge is, causes the shelf life of our traditional, sometimes education and skill sets can become shorter, causes engineers to become obsolete if we don't continue to learn and progress over time. It's particularly true if engineers do not, if we don't develop our skills and knowledge base. So that's a big part of why continuous learning and updating of knowledge and skills is very critical to the success and career continuation of an engineer. The National Academy of Engineering recommended that, and I quote, "In addition to delivering content, engineering schools must teach engineering students how to learn and must play a continuing role along with professional organizations in facilitating lifelong learning, perhaps through offering executive technical degrees similar to executive MBAs." It's an interesting perspective and something that probably is a good idea for all of us. Professional development hours in Michigan are regulated through LARA. For more information on these, see the michigan.gov website for LARA. But we'll kind of just briefly touch on these. Most of you are probably very familiar with this. Licensees are required to complete 30 hours of continuing ed per 24-month period. These 30 hours of continuing education can be compiled during the 2-year period prior to expiration of their license. A minimum of 2 hours must be earned in ethics. We're getting you one here as it relates to professional engineering. Unfortunately, any hours above and beyond those 30 do not carry over to subsequent years. Licensees shall maintain records of their completion of the continuing education for 4 years from the date of filing renewal of the license. And licensees may be required to prove records to the department upon a request as a potential audit. All right, we'll close out here with a brief case study from Florida. It's the FIU footbridge in Miami. The FIU pedestrian bridge was designed to be innovative, signature bridge for the university. Unfortunately, during construction, the 950-ton span collapsed, injuring 9 and killing 5. A key concrete support truss in the bridge developed worrisome cracks 10 days before the structure was lifted into place. The blue hydraulic jack shown in the top inset photo was attached to a tensioning rod running through the bridge's number 11 strut, concrete brace that helped support the span in order to retension the structure. It's not clear why workers were doing this, but independent engineers believe the procedure caused the number 11 support to fail. Thankfully, the collapse happened before the bridge had been open to foot traffic. However, there was still traffic traveling under the bridge when it fell. The collapse was being investigated by the National Transportation Safety Board. Several independent bridge engineers were asked by the local news to review the designs, and they all found that cord 11 was too small and lacked adequate reinforcement. Unfortunately, part of the aesthetic design didn't allow for redundancy in the design. For example, there was only a single truss, and what appeared to be cable stays were actually just used for lighting. The ethical dilemma associated with the collapse, in addition to the questions of design, is whether it is a breach of professional ethics standards for professional engineers to give opinions on any aspect of a construction accident. The spokesman for the design group claimed that any opinions made public by other engineers were in fact speculation and a breach of professional standards. However, NSPE weighed in on the tragedy and said that independent engineers are often used to shed light on tragedies, such as Hurricane Harvey or the I-35 bridge collapse in Minnesota. According to NSPE, it is not in fact a breach of professional standards, as long as the engineer has studied the facts and circumstances of the incident and is properly trained. Here's a list of some additional resources as far as ethics are concerned. ASC has and NSPE both have some pretty good pretty good case studies and topics regarding ethics. Space shuttle Challenger disaster. The Hyatt Regency walkway collapse is really pretty neat. Wasn't able to get that one in here. NSPE has some really good case study videos and the You Be the Judge section for you to check out if you so feel like it. But I think that's all I have here today. I think we're about on time. I would have much rather done this in person with all of you guys and kind of get a little more feedback and have a see some reactions and see what you guys are doing. But nevertheless, it's still good to go ahead and get this in. I'm glad we were able to, Steve.
Yeah, I am too. Thank you, Jeff. We appreciate your time this morning and talking about this for our attendees and the folks that were able to at least make it today from the cancellation of the workshop in Kalamazoo. So if there are any questions that you have for Jeff or any comments, feel free to type that in the chat window. It's probably the easiest in the chat and send everybody, or you can type a specific question to Q&A. That option should be available in the Zoom control panel there. But not seeing anything as of yet. Thanks everyone for attending this morning. Now that this will conclude our webinar series that we had to scramble and put together. So we'll start issuing attendee certificates to those that attended. So you can maintain that for your files. And all of these presentations and webinars will be available on our website in the near future as well. Probably this one, probably in the next week or so. And it should be linked from our homepage. Otherwise, if you just Google Michigan Concrete Association webinars, chances are you'll be able to find the link to it on our website, miconcrete.org. So thanks everyone for attending this morning. And thank you, Jeff. We appreciate your time and effort in giving this. And if anybody has any further questions, feel free to contact us or Jeff if you have any questions on this topic or other concrete related issues. So thanks, everybody. Take care.
Take care. Thanks.